Hello and good evening, everyone. Welcome. I would like to welcome you all to the Smart Grid and Microgrids webinar series. This session is the topic of this session is incorporating hydrogen storage with renewable energy for microgrids. And this webinar series is organized by the Smart Grid Research Group in the Department of Electrical Engineering of the University of Moratuwa. My name is Kalhan Borlessa. I am a PhD student and a research assistant in the department, and also I'll be the host for this session. This is the sixth session that we are having in the series, and we did some sessions on distribution system automation, microgrids, and microgrid control, and also we are planning to do sessions on microgrid protection, planning and design. Also modeling, and also there are sessions on AI applications in smart grid. Today our presenter is engineer Anupama Silva. He's a chartered engineer with 18 years of experience in the industry, and he had obtained his BSc engineering degree in electronics and telecommunication engineering and the MSc degree in electrical installations from the University of Moratuwa. In addition to that, he holds an MBA degree and had certified as a project management professional by PMI USA. He presented his research paper at IEEE conference, specifically ICPES, in 2018 on hydrogen energy and its applications. Without further ado, I would like to invite engineer Anupama Silva to continue the session.
Good evening. May I share my screen first?
Yeah, sure. You can share.
I think it is visible to you.
Yes, it is. It is.
Good evening, dear Professor Udayanga Hempalatha and our coordinator, Mr. Kalhan Borlessa. Thank you for inviting me to do this session. First of all, as the first session for the year 2022. Also, I'm happy to have that invitation because it's, however, I'm a product of University of Moratuwa, and there's nothing any engineer can have a pleasure as such getting an invitation from his own university to do a webinar. Thanks for both of you and SGR group as well. I think Kalhan has introduced me, but with that, do not keep any hesitation to disturb me, even if you need something to be clarified in between. I'm fine. You can disturb, but it is better if you keep your questions to the end, to the Q&A session. But if it's really you are with the curiosity, you can disturb me and ask. But I really like if you can ask some questions. Keep that interaction with the session. So I'll start. Our topic today is that incorporating the hydrogen storage with renewable energy for microgrids. If we go forward, let's see that what we are going to discuss today. So as the roadmap, when I was having a discussion with the organizers, that I got to know that the audience has a vast area, the vast range of audience, that from undergraduate level to the postgraduate and PhD level. So I thought of starting it from the beginning. Let's discuss some green energy. We can identify what is green energy and why NCRE, what is NCRE, and the importance of energy storage. Before come to the hydrogen storage, we should know, we should understand why the energy storage is required. And then when it comes to the hydrogen storage, I would like to give some introduction to the research and the findings and the conclusions we arrived at of the research, and what are the available options for the hydrogen storage and challenges and how to overcome them, and what will be the future of hydrogen storage. I hope to carry you through this road, and I gave you the map. We'll see that how we go through. NCRE, many people talk about that. Though they are referring it to NCRE, some people know what is NCRE, some people don't. That NCRE is non-conventional renewable energy. Before coming to the non-conventional, let's discuss about what is renewable energy. This renewable energy, those are the ones which do not emit carbon dioxide from the sequestrated, carbon dioxide which was sequestrated some millions of years ago. And these are renewable, means they use it as we get it. That is why it is renewable. When it comes to the electrical energy, we divide it to the non-renewable, we segregate into two. One is non-renewable energy, the other one is the renewable energy. The non-renewable energy are fossil fuels. The fossil fuels are the ones which had been, with the time, many amount of carbon dioxide had got sequestrated and kept under the earth. And now those have been converted into the fossils, and we are now mining. We are mining them and getting out, and we burn to get the energy stored in those fossils. Those are fossil fuels. For example, not with high technical terms, all the crude oil products, that's petrol, diesel, all these and coal. All these falls under the fossil fuels. The other one is the renewable energy. Renewable energy, we can segregate again into two segments. One is the conventional renewable energy. Say, for example, large hydro. If you take Victoria, Rantabe, Randenikal, Mahaveli project, all these are categorized under large hydro. Those are conventional renewable energy sources. We have considerably large storage reservoirs, and then those potential energy stored in those reservoirs are converted into kinetic and then converted into electricity. Those are called conventional renewable. Then what are non-conventional? Non-conventional renewable energy sources are the solar PV, the solar and wind, small and mini hydro, biomass. All these are categorized under non-conventional renewable energy. Why we say it as non-conventional? Those cannot provide a much larger amount of energy as we require. We'll see why is it. Again, now we are coming to the shortened form, NCRE. Why we need NCRE? These non-conventional renewable energy sources, before 50, 60 years, 5-6 decades ago, no one were interested on these small hydro plants, mini hydro plants. No one was much interested. And wind energy, those plants were used for very localized operations and not with high efficiency or something. Or maybe in some plantation they might have used some sort of small scale, even with some generation even below 1 or 2 kilowatts, some 50-60 years ago. Now the reason here is, now the researches are being done on NCRE because the world is now approaching towards some scarcity of fossil fuels. And on the other hand, the global warming had become a severe problem as identified by the scientists, and even ourselves are now feeling it because of the emission of greenhouse gases. The global temperature is being raised. So there's a concept called carbon footprint. The amount of carbon dioxide, weight of carbon dioxide emitted by a person, that we referred it as an index, as carbon footprint. And when we are talking about this GHG, greenhouse gas emission of greenhouse gases, when reducing the carbon dioxide plays a great role. It accounts for a greater share among the greenhouse gases. We know the CFC, chlorofluorocarbon, methane, all those are categorized under greenhouse gases, but among all of them, the carbon dioxide plays owns a considerable share out of that because of the working activities of the humans, basically because of the energy production. The other one is the conventional renewable energy sources. If we are facing a scarcity of fossil fuels and we are going towards emission of emitting carbon dioxide, why we can't go for further conventional renewable sources? The reason is, as of now, a considerable share of conventional renewable sources had been utilized, have been identified, and they are being utilized as at now. So the scarce now the world scientists and all the researchers are being now channeled towards the explosion of the NCRE. There are several heights when we come to NCRE. Some people say the solar is coming free to earth. We have ample amount of bare lands, and we are a country. If we come to Sri Lanka, we are a tropical country, and we receive enough amount of sunlight, direct sunlight that we get, not like the European countries. But some people say European countries, even though they do not get a sufficient amount of direct sunlight, they harvest the solar energy. But why Sri Lanka cannot? Why Sri Lanka don't? People think this solar energy as free. Is it actually solar energy is free? Yes, solar irradiation is free. We receive it for free. With that, from our ancient days, we have used solar energy as free irradiation for drying of our clothes, drying of some food. Yes, but for electricity, there's a concern. We'll come to that. Potential of waterhead. Yes, those are renewable NCRE. The potential of waterhead is free. Then no one charges us for the waterhead. Yes, it is free. And if we go to the area of Kalpiti, Pulam, Hambantota, those areas that we get, even in the Riverstone, we get free wind blows. The wind kinetic energy contained in strong wind blow is free. Then can we term it as that NCRE is free or very cheap? If it is really, then the question comes, if it is really free, then why not being vastly used? That's the question. And it's our duty as engineers and researchers to find ways and means to get this free energy, free incident energy harvested at the lowest cost. Then why this lowest cost matter comes? If the incident is free, not only energy matters, the reason is the form of energy is the concern. The conversion of energy from its one state to the other state, it requires higher capex. When it comes to the audience of our undergrads, capex is capital, the capital expenditure, the short form in the industry we use as capex is the capital expenditure that we use. That all these solar irradiation, potential of waterheads, and kinetics in wind blows, all those are the operational. Those are received free. Like those are the fuel that we get into these NCRE systems. Those comes as the OPEX, the operational expenditure, like the fuel. If we pumping our car with fuel, or we are pumping diesel to our generators, this solar irradiation, potential of waterhead, and kinetics in wind blows, those are like that fuel. So those comes as the fueling cost. That is OPEX. Only the part that what we get as free is that OPEX part. That free fueling part is we are getting as free. But the conversion mechanism, the conversion machines, say for example, so the solar panel is not a machine, but it's a system. Those conversion systems requires a higher amount of capex. That is the reason why not these NCRE are not being vastly used as at now. But world is changing, world is doing researching to get the maximum benefit out of these freely received fuel. That is the reason. So if someone asks you as engineers that you have to engineer students, practitioners, the simple answer, but you have to give why these NCRE cannot be harvested towards energy is very simple. The energy is fuel, it is received free. Even though it is received free, the conversion mechanism requires higher investments. Those investments means we need returns out of investment, that is return on investment. If the harvested energy is sufficient to recover that invested amount, then only we can implement those systems even as a country or even as a business. That is the concern is not the freely received energy, the form of the energy is concerned. Say for example, if you want to get your clothes dried after washing, yes, you can use the free solar irradiation, but it does not mean you can get your shirt or your dress ironed using the free solar irradiation, because you need to convert the solar irradiation into electricity. Then you have to power your iron to iron your clothes. I think you could get some understanding on what is NCRE. Is it free? What portion is free and what portion needs to be pumped with money? Why the importance of energy storage comes? The electricity generation is divided into basically two based on the nature of the generation. First part is dispatchable, the other one is non-dispatchable. Then what do we mean as dispatchable and non-dispatchable? Dispatchable means the system or the controller has a control over the controlling of the generation, controlling and distribution of generation. If the particular source of energy gives that control to the controller, then those generation types are categorized as dispatchable. Yeah. Say for example, if you take our one and only coal power plant at Moratuwa, it's a separate story. At any time that if we ask these days, two machines are not working, but it's a separate thing. But however, we can control, are we taking the full 300 megawatt of one machine out and give dispatch it to the grid, or are we controlling it to 200, 250, 150 based on the demand? We can decide it. Say for example, in our large hydros, the controller can limit the size of speed or energy of the jet, power of the jet, and control the generated amount of electricity. LNG is also same. But say for example, if we go to mini hydro and micro hydro, we can control, but those water streams are not highly available at its optimum level flow on every period of the year. So those because of the capital investments done, and to recover those investments, the best recovery is given when, if the generated electricity is taken as it is generated. Let's say for example, for rainy days, the CEB has to get all the generated energy out of these mini and micro hydros, unless those energy will be wasted. So at that time, the controller has to reduce the output of dispatchable plants and make the maximum use of non-dispatchable plants. Say for example, wind. When at the time that wind is not available, you can't make the harvesting. But when the wind is there, then you have to take the full amount which is generated through those plants. Solar PV is also same. But when it comes to solar thermal, the third picture, here we take the third one, it's solar thermal. It's solar. Solar is some non-conventional, but solar thermal can be termed as dispatchable because it uses the heat, it stores the heat energy, and we can use it as dispatchable as we need. But solar PV is not like that. Solar PV is categorized under non-dispatchable. When we are dealing with these non-dispatchable sources, then we need to have the elements for storage, because when we have the production, we need to store the excess, and then at the time the excess production is less, we recover the earlier stored excess production at that time to balance the supply and demand. So that is why the energy storage are important when it comes to the electricity generation with non-dispatchable type of sources. When the non-dispatchable energy comes, this non-dispatchable energy sources say, if we are going with them, we need the storage. The means of storage are very, one types are batteries, and here is some capacitors. This solar that heat storages, liquid heat storages, and hydrogen is the other means of storage. It's gas or liquefied or metal hydrides. We have options, and our topic here is we come regard to this topic of hydrogen. I would like to say that the research I have done, was to test the analysis of using on-site hydrogen production using SGRG and power up some off-grid telecom base stations. The reason for this is, in general, the Sri Lankan context, there are many telecom base stations. The operator that I have used for, that is a leading telecom operator I used for this research. At that time, there were 3,000 plus sites owned by them itself. Out of them, some sites are not in a position to get the grid powered connections. So those sites are run on 100 full time on diesel generator power. And there were some approaches tried time to time to use the solar power, solar PV, but with a very fixed configuration. The existing setup, it was with 2 kilowatt solar panels and with 10 kilo kVA of diesel generators, and with around 100 ampere-hour battery banks that they run it, and that was the setup it was. And what I wanted to test here was to use utilizing the attributes of the problem. I wanted to check how we can use this solar irradiation coupled with the hydrogen storage to reduce the power OPEX of those sites. Actually, it is the optimum power cost was the target. The major attributes that you know that if we come to a telecom service, that we do not prefer to have a connection from an operator who does not maintain the network properly. That we need the availability. That means the power supply is very essential. The availability of power supply is required for 5 nines. That means 99.999. But for an off-grid site, a specific site, so 3 nines will be sufficient. That was the expected attribute of that. In telecom base station, generally the load pattern is constant. So that was taken as a plus point towards this approach. And also the off-grid sites are not planned to be with high loads, because those sites are just to cover the coverage spots, but not to use as the repeater stations or some transmission backbones which uses high power, no many multiplexers. So those are attributes. Those attributes actually worked as some positive parameters towards this approach. We'll see that what we have done. The proposed solution the source of energy was taken as the solar PV, photovoltaic, and the means of storage we taken as compressed hydrogen. When it comes to compressed hydrogen, we should have the compression, the storage, and again regeneration of electricity through the hydrogen. And the hydrogen is extracted through the process of electrolyzing. This electrolyzing process is powered through the solar PV. And also the compression also sucks some sort of energy out of the production of the energy. Here, the earlier setup, here we had only 3 components, but here we have many components. That means some additional capital investment is required. But then what was the approach to take the cost down in the industry or in the country or whatever, any investment, the investor expect a return. Without that return be positive, the investor won't invest. That's the key. The engineering students, when doing research, this is a key to be in mind. But for researching, it's fine. We can do any fantastic thing. But when it comes to the implementation, the researcher should come with some solutions which are practical in terms of cost. That without the concern on cost, without solution based on cost, a researcher won't be a practical engineer. A practical engineer is one who knows the technology, who knows the researching, and who knows what is the sweetest compromised position, sweetest blend between the technology and the cost. So what I have proposed here, to omit this battery bank, why it was selected, batteries, when we have some deep charging discharging cycles, the lifetime of the battery depends on majorly depends on number of charging discharging cycles. When the operation is done based on this scenario, these batteries undergo very frequent charging discharging cycles, and it very early, it ends its usable life very early. Again, the replacement requires. The replacement requires means it is again pumping of capex, capital expenditure. Those are the plant maintenance capex. There are several types of capex we refer to in the industry. And the maintenance is operational expenditure that hits directly to the profit and loss of the company. So what I wanted to do is save that operational expenditure as well as repetitive capital expenditure by omitting this battery bank. The hydrogen storage was the alternate solution to take the means of storage in the solution. On the other hand, the other one is I tried to resize the diesel generator. Here it's fixed for any context, for any load, for any irradiation pattern, irradiation intensity. The diesel generator which was used was fixed as 10 kVA. I have no clue that how that figure was taken, but maybe that is the one the procurement is doing for majority of sites. So it may be for easiness of the maintaining of spares and those aspects. It might be the reason, but it is not cost effective, because if the demand is less than 60-70% of the utilization of the generator is 60-70% of its maximum capacity, then the efficiency of the operation of this generator, it comes low. So it is not healthy for the operational expenditure. We need to keep the efficiency high. So if we can size this generator at the appropriate value, which suits for the operation of the site, the load pattern of the site, in that means then it is a reduction in capital expenditure. On the other hand, higher the rating of the generator, again the maintenance cost is higher. So in that means that I tried to optimize the size of the diesel generator and optimize the fuel consumption of it. Here we explain it. The removal of the battery bank it is replaced through hydrogen, and this large size generator, diesel generator, is replaced with the smaller one. We'll see that basically the research. I'll come to that. Then again, whether this solution is successful or not, how to decide? Two aspects. One aspect, first of all, whatever the cost, whatever the commercial benefits, first it should be technically feasible. It's the role of the researcher. First, we should test and prove whether the solution is technically feasible. How we do it? We should meet the energy demand, power demand, as well as the availability. It is no mean that if we meet, though we meet the power demand, if we can't meet the entire energy requirement throughout the year, the entire energy to the entire span of a year, so it's no point that we have failed in terms of availability. And the system robustness towards the failures is one of the other technical aspects that we need to consider. So to be the system to be technically feasible, we need to test against these parameters whether we are in par with the demand. The other one is the commercial viability. If the commercial viability is not there, then the investor won't invest. Then this particular project will not be funded by the operators to if they do not get the sufficient return. The return on investment, we terms it as ROI. Whether the capex we need to check whether the capex is recovered, the OPEX is reduced, whether is the IRR are healthy, or what is the payback period. There are several aspects, several ways, several indices that we are taken to measure the ROI, net present value, simple payback period, internal rate of return. Those are the indices that we used for that. Again, we have to check whether it is down. The ultimate expectation of the investor for that is the bring its cost down. When it comes to businesses, other than for the corporate social responsibility projects, the carbon footprint and the green energy, those are some fantastic topics for the investors. They are not investing their money if it is not for two aspects. If it is not corporate social responsibility project, they won't look at that. If the cost is not coming down, if they have the return on investment, they will do it. That's the very simple theory when it comes to investments. To validate this, we have derived some equations, the bit complicated mathematical equations, and we did the calculation through this. The energy for all of these elements that we introduced into the system: solar PV, fuel cell, hydrogen storage, converter, and electrolyzer, diesel generator. These are the elements. But for everything that we have derived the equations to calculate the amount of energy produced and the energy losses and the energy consumptions. And not limited to that energy part is being calculated to test the technical viability, and to test the commercial viability, we need to calculate the what OPEX component of the particular element while it is at operation. So that is done. We used Homer to model the system, and at the research, I have defined 9 test cases with for 3 locations extracted from selected from various geometric and climatic areas of the country. For this webinar, I have selected one location is in Kurunegala district near Mahava, Amunakole. The base station's name area, the localized area's name is Amunakole. the solar irradiation pattern is like this. The 3 test cases I have taken here was derived based on this. If you see the graph here, the number of base stations tabulated against the consumed DC power, you will see when the entire network is taken, the majority of the sites, it's a left skewed bell curve. You will see this is a normalized bell curve, that is normal curve skewed to left. That means the majority of sites, that more than 2/3 of sites are consuming less than 2 kilowatt. It is obvious for these 8 to 9 kilowatt sites, 4 to 5 kilowatt sites with 4 to 5 consumption 4 to 5 kilowatts, that we do not need to touch those with this renewable energy. They're not necessary. Say for example, if we come to again telecommunication engineering, the reason behind for this high consumption, high power consumption, is due to those sites are repeater sites, maybe the base, maybe some hub sites with some critical operational requirement of the network. So it is not advisable to touch for these type of things if at present, if those sites can be powered through the grid. But we need to find the positions which we can use our solutions, our novel solutions at a very optimum operation, optimum cost. So that is what I have done. There's no point that we address this solution to this tail, the right hand tail or middle. But here we have ample amount of opportunities to check whether this is viable and to implement and harvest if it is viable, to then harvest the opportunity at the majority of number of sites. We see that majority of sites fall between 1 to 2, below 1 to 2 kilowatt. So case 1 was defined as 0.5 kilowatt, case 2 is 1.5, and for be very rational, the case 3 was taken outside of that to test whether even if we needed, it is viable or not. So the viability test case, if say for example for the case 1 for this particular location, when the load is 0.5 kilowatt, the Homer modeling, it gives very simply you see the diesel generator had not produced a single kilowatt hour. That means we see here the number of starts for the diesel generator is 0 for year. That means for this setup, the diesel generator had not even started. The 96% of the energy was purely pumped through the PV array. This remaining 4% was pumped by the fuel cell. That means hydrogen storage was used to 4% of energy. When the fuels come to fuel cell, the fuel cell has operated nearly 52% of the time. That means maybe for the time which does not have the solar irradiation, it's very low load side. So it had discharged its energy throughout the night time, and maybe it operated to 52% of the time. And very simply, so hydrogen storage is responsible for 4% of energy at this time. The hydrogen storage delivered this amount. It is, and also that we see the unmet load. The unmet load is very minimal. That means the energy requirement had of the demand has very sweetly met by the system. So we can, with this unmet load figure, we can say this under this test case, the system is viable, technically viable. And when we see that our size of the generator is very smaller, one is enough, and PV array is 30, we are omitting the OPEX of battery bank, capex of battery bank, opex of and capex of both of large size of generator. So when it comes to commercially viable, it's not very straightforward. We can say it at a later slide. I'll explain you with the sensitivity analysis how we arrive to this viability of in terms of commercials. And similarly, for the test case 2 with 1.5 kilowatt load for the same location, the PV again at that time the diesel generator has operated, and it accounts for a share of 15%. But the size of the diesel generator is just 2 kilowatt. That 10 kilowatt generator was actually a waste with the traditional setup. Generator has operated 50-50 generator and the fuel cell. It has operated nearly a similar portion of time, but the amount of energy delivered through those elements are different. Diesel generator accounts for 15%, while the fuel cell accounts for 2%. Then when fuel cell accounts for 2% means our hydrogen storage has delivered 2% of energy share. Unmet load is also again still very minimal, so it is technically we can say it is technically viable. And for the 2.5 load, again we see the what we see is say for example when it is 0.5, the fuel cell accounts for 4% of energy hydrogen storage. Then when it comes to 1.5, it reduced to 2%. When it comes to 2.5 kilowatt, the higher the load, the share of energy delivered through the hydrogen storage, it diminishes. It is again 1%. Still, the proposed methodology is technically viable with this very minimal unmet load. When we come to the summary and the conclusion against the test results, solution is technically and commercially viable. How we see the commercial viability is yielded basically optimizing the diesel generation, generation of the diesel generator in size and reduce the operations time. Then that means OPEX is drastically taken down by reducing the usage of fuel and increasing the efficiency of operation by taking the size rating of the generator reduced, and the maintenance through everything when it comes to the maintenance of the generator, the OPEX is reduced. Then omission of the battery bank, and the repetitive, with that we omit not only the battery bank, the repetitive replacement of the battery bank is also omitted. It's a considerably higher cost, and on the other hand, it is a saving for the environment as well. So that commercial viability, the saving for environment does not account for commercial viability if we do not take it as the into the balance scorecard of the company, but separate story. And the hydrogen storage. What does hydrogen storage do? Towards this viability, hydrogen storage had enabled the omission of the battery bank. It provided the room for to avoid the battery bank by taking the responsibility of the storage function, and but hydrogen storage had not taken the entire energy requirement. It just enabled reduction of some operational expenditure. The responsibility for converting the cost rescaling into viability, and because of that the initiation of introduction of hydrogen storage, this cost rescaling was made viable, both technically and commercially. If this storage was not there, this option was not selected, what will happen? There's no any way to manage the energy requirement when the solar is non-dispatchable. And this is a good eye-opener for the researchers, that we should be taking a very selected part and addressing that particular small positive points of a problem, we can achieve a higher results rather trying to solve very large problems. Best example is here what we have done. we have selected only a very few portion. We are reducing OPEX drastically, and also for a large volume, we are applying this solution for a larger volume. So even our reduction of cost or our reduction of even, say, for example, the carbon dioxide emission is small, but it accounts for a large output because our volume dosing is higher. So that is a good eye-opener for researchers. On the other hand, the context of when we come to the context of hydrogen storage, here under this research, what we have done with hydrogen storage is we used compressed gas hydrogen. But is that the only option that we have to use with hydrogen storage? No. What are the advantages here we do? We get the advantages with this method, hydrogen storage, we consume what? We consume water. At the electrolysis process, we consume water. And for the electricity generation process, again, we consume oxygen. The stored hydrogen is sent through the fuel cell and it reacts with the oxygen in the atmosphere, and while at that reaction it generates electricity. That's the way. But what are the byproducts? While we are consuming water at the electrolysis process, the byproduct is oxygen. Oxygen is not harm for the environment, not harm for the human being, not harm for the livestock. And the other byproduct is while at the electricity generation, the other byproduct is water. We see here it's a cycle. At the electrolysis process, we consume water, but at the electricity generation process, as a byproduct, we get water. Our main product is electricity. And at the electrolysis process, we generation process, we consume oxygen, but the same oxygen is again released while at the electrolysis process. So it is a cycle. The only thing is, for base, when we are going through this cycle, an energy also being consumed for that. That is one of the disadvantages. I'll come to that. But with these two byproducts, oxygen and water, they are not harm for environment, and this is zero carbon emission. This zero carbon emission means this does not involve with any carbon dioxide activity. So it is zero carbon, but it is not carbon neutral. It is zero carbon. That's the main advantage we can say as this with this hydrogen storage. But it is to be zero carbon. This entire hydrogen, not only production, storage, hydrogen production should be from renewable energy. If and only if it happens that we can say this hydrogen is green hydrogen, unless if for some compression or cooling or whatever process, if we use the grid electricity, which is generated through fossil fuels, then that particular hydrogen, even we take the hydrogen as through electrolysis process, those type of hydrogen production cannot be termed as green hydrogen. So that's some other terminologies that we have to refer when it comes to the discussion of hydrogen. The other advantage is the energy density of hydrogen gas is 2.8 times larger than that of diesel. That means when it comes to weight by weight, the energy contains in 1 kilogram of hydrogen is 2.8 times larger than the energy contains in 1 kilogram of diesel. What are the disadvantages? The disadvantage is this hydrogen is highly inflammable. So we have to take safety measures. When it comes to the gas safety, these days we know what is happening with the gas safety. So it is highly flammable. So we need to take some safety measures, but it is once we get used with those, so those will not be much difficult, but we need to incur additional cost on these measures and the transportation cost. But this transportation cost, though it is a cost, but for the transportation itself, the hydrogen storage is being used. The fuel cell cars, the fuel cell vehicles, the fuel cell trucks, those are the fuel for those are the liquid hydrogen. So, but the concern is for the transporting, when this hydrogen is transported, then the safety measures are to be taken. And if it is compressed as a compressed gas or liquid hydrogen, it also consumes energy. The energy which we could have used for some other aspects, we have to use it for the compression or the liquefaction of the gases, hydrogen gas, and we say it is as an disadvantage. And are we limiting by these disadvantages? No, that is the scope of the researchers. The workarounds, we are finding workarounds for transportation cost. What the best we can do is we are going towards the on-site production rather than producing it centrally. We do the production on site through solar irradiation or wind, whatever. We do the production and compression at the same site, the on-site production, as I did for under the research. The other one is the liquid organic hydrogen carriers. That means there is some catalytic solutions. We use the dibenzyl toluene, that some organic material, and that is the emerging way of hydrogen storage for the future. Not limiting to liquefaction or compression, but these are once these materials are used, when the high density gases are being contaminated through these organic materials, then it extracts the hydrogen, and the purification of those hydrogen is said to be at a very considerably high value, and those storages are at the stable state, so not inflammable, and it is not require very low cooling, and it will be the future of the hydrogen storage related researchers and production for the research areas in the future. I think that's done. If you have any questions, it's open to you.